Let us take question number 10. In question number 10, there is a rigid bar which is connected to 3 members. 2 are made up of brass material. The third one is made up of steel material. This is the rigid bar. These two are brass materials. Seems to be columns. Exactly at the middle, there is another member which was connected, which is made up of steel. Now, for the rigid bar, these 2 points are taken as A and B, and this point I am taking as a C. Exactly at point C, there is a concentrated point load which is acting with the magnitude of A. So there are 3 bars are there here. 2 brass materials, one is steel bar, and AB is a rigid member. The definition, everything I am going to discuss later. In this question, the area of these 3 bars, the length of these 3 bars is same. That was given in the problem. And at the same time, the Young's modulus of steel material is given as E, whereas the Young's modulus of brass material is given as a 2 times of A. And in this question, our aim is to calculate what is the total displacement of point C, downward displacement of point C. What is the total downward displacement of point C that need to be calculated. So just to calculate the delta C, if you know the concept and if you know the relation, so delta C is exactly equal to delta of steel material plus delta of brass material. So because of this load, the rigid bar will move downward direction. The rigid bar will move downward direction, let us say by 5 millimeter. And because of this load, the steel bar is having its own deformation, let us say by 10 millimeter, for example. Because of this load P, the rigid bar will move downward direction, but that will not be visible to our naked eye. So the random values I am giving. So if the rigid bar moves by downward direction by 5 millimeter, point C will also move by 5 millimeter, and because of own displacement of steel material, point C will move again downward direction. So this will be the net 15 millimeter. So from this relation we can form this equation right here. So delta C, delta steel plus delta of brass. Delta of steel, PL by AE is the basic formula. So PL by AE is the basic formula. This is for steel material plus PL by AE. This is for brass material. As we already know, for steel material, what is the load which is acting? P. Length is L divided by A multiplied by E of steel material, there was given as a E, plus the load which is acting on the brass material, each brass material. Keep it in mind, exactly they said the steel bar is connected at the middle. The steel bar is connected at the middle, then the total load is equally distributed by these 2 brass materials. Then on each brass material, the load is acting as a P by 2. P by 2 multiplied by length of brass material is a E, area of cross section A, but E of brass material is given as, sorry, not 2E, E by 2 is given. Actually, E of steel is greater than E of brass. So E of brass is E of Young's modulus of steel material divided by 2. So E divided by 2. So divided by 2 both will be cancelled out here. PL by AE, here also PL by AE. So finally you will get the answer as, sorry for this relation, this is correct relation my dear. E of steel generally greater than E of brass. So this will be 2 times of PL by AE. So this is the correct answer for this question. PL by AE here, PL by AE here. There was given option 2, PL by AE, PL by AE, PL by 2 AE, like that there was given some of the options. This is the correct answer for this question. But the person knows the concept, easily by using this relation they can do. But the information that I am going to discuss and how this formula came. So before going to that, some of the assumptions that I am going to consider, assumptions which are required to solve this question. Those assumptions are, before and after deformation, the rigid bar should be in horizontal. The first assumption. As we already know, the rigid bar, for the rigid bar, the steel material exactly connected at the middle. This is the reason why after the deformation also, the rigid bar still remains in horizontal position. It should not be in inclined position. It will be in horizontal position. So that is one of the assumptions. And the second assumption is, before going to that, do you know what is meant by rigid bar? The definition that I am going to discuss. Let us consider a material. Inside the material, I am considering 2 points. One is A, the other one is B. In between these 2 points, the distance I am taking as X. Internal points, the distance between the 2 internal points that I am taking as X. Now, this is the condition before the application of load. But now, if you apply the load in several directions with the different magnitudes, one may be towards it, one may be away from it. If you apply the number of forces in different directions with the different magnitudes, even though the distance between these 2 points should not be changed, X never vary, never changes. before and after the application of load. That type of body can be called as a rigid body. If it is not a rigid body, do you know what will happen? This rigid bar, if it is not a rigid body, then AB member will deflect because of this load. So here there is no deflection because the AB is a rigid bar, right? If X changes, that body can be called as deformable body, right? So the basic definition of rigid bar. Is there any existence of rigid bar in the universe? No, there is no existence of rigid bar in the universe. But under certain load limit conditions, again I am telling, under certain load limit conditions, the body is assumed to be a rigid body, right? So keep it in mind. Whatever the analogy that we are doing, not only strength of material and theory of machines also, the members are not the rigid members, but those should be a resistant members. Resistance means up to certain limit they should act as a rigid. So those are called resistant members. A belt is the best example for a resistant body. For the resistant body, deformations will be there, but those are in very negligible limits. Right? So a member may not be a rigid body, but it should be a resistant body, right? So that one of the necessary condition. Now, one more assumption also that we need to consider. Because of this application of load, whatever the deformations which are happening inside the steel and brass materials, those will be in the elastic region only. So all members are elastically deformed. If the deformation is permanent, then these formulas should not apply. There will be another analysis, right? Now, in another way also we can form this equation. Let us take the same rigid bar AB, but here the bars I am replacing with the springs. These are the two springs that I am replacing with two brass members, and this is the another spring which will replace the steel bar. It is subjected to the magnitude of P here. So let us say this is 1, this is 2, this is 3, and this is the rigid bar. So from this also we can say the net deflection of point C will be delta 1 or delta 2, both exactly equal, plus delta 3. Keep it in mind, if the two spring displacements are exactly equal, then what we can say, 1 and 2 are in parallel arrangement. There will be a topic called springs. In the springs we are going to discuss springs arrangement. Any problem came there also I am going to discuss. Now this 1 and 2 parallel connection is connected to the third spring in series arrangement. 1 and 2 are in parallel arrangement, but these two are with respect to 3 in series arrangement, right? So that point you need to know. So because of this load, the rigid bar will move in downward direction. These 1 and 2 springs will be compressed, right? But third spring will be elongated, right? So the net displacement of point C will be this one plus this one. Now how this formula came? Delta as PL by A, elongation as PL by A. How this formula came, that I am going to discuss, right? Yeah. For that, let us consider a member which is subjected to an axial tensile load. What is meant by axial load? Axial load is nothing but which is passing through the axis of the member. That can be called as axial load, which is passing through the axis of the member. It's an axial load. If it is perpendicular to the cross section, it can be called as a normal load. If it is away from the cross section, it can be called as a tensile load. Different names are there. Keep it in mind. Now initially the length of the bar I am taking as a L. The cross section area is A. So the point is, because of this application of load, if you consider at any cross section, at this cross section, if you observe in a microscopic manner, the atoms are arranged like this. The atoms are closely packed together inside the lattice. So between these two there is an atomic bond. Between these two also there is a bond strength. So because of this application of load P, these atoms wants to move in the rightward direction, but the left atoms will offer some resistance to it. So this is the plane where resistance will offered by the material. So again I am telling, because of this application of load, these atoms wants to move in this direction, but these atoms will offer some resistance because there is a bond strength between these two. At the same time, because of this load, these atoms wants to move in the leftward direction, then the right atoms will offer some resistance. If you look at from the side view, the resistance will be offered throughout the area. So that area can be called as resisting area. So here there is a definition coming to the picture. For this cross section, the rightward direction, this is application of load P. From each atom, the resisting forces I am taking F1, F2, F3 and so on. If you sum up all these things, this should be exactly equal to P because it is an equilibrium. Exactly. If P is more than the internal resisting force, it will be move in this direction continuously. If internal resisting force is offered by the material, keep it in mind. Now the material is still in rest position, that means equilibrium. So exactly applied load should be equal to the internal resisting force. But the material is having maximum capacity to offer some internal resistant force. Keep it in mind. So maximum F max, what we can call it as F max, the total maximum internal resisting force can be offered by the material, can be bared by the material. This is what exactly called a property. Stress is not the property of the material, keep it in mind. So here that I am going to discuss, my dear, whatever the resisting force offered by the material, that is exactly equal to P divided by the resisting area or per unit area, exactly what we can call it as stress. The symbolic representation is sigma, right? So if anybody asked in the interview, stress is defined as an internal resisting force offered by the material. Again I am telling, internal resisting force offered by the material against to the deformation because of the externally applied loads. Is that clear? The perfect definition for your stress. Internal resisting force offered by the material. It will be offered by the material. Against to deformation. Because of externally applied loads. Look at the definition once. Because of the externally applied load, there will be a deformation. Because of the deformation, there is a resisting force. This resisting force, which is acting just per unit area, is the term called stress, represented by sigma. But one more point I am going to discuss, my dear. Let us say inside this material, at the particular cross section, there is an internal void. If internal void is there, this will not offer any resisting force. So keep it in mind, here more resisting force is offered by the material, but here less resisting force is offered by the material. The resisting force which is acting per this cross section is non-uniform. So non-uniform because of this internal void. Internal void is nothing but there is an air gap. So this air gap are coming to the picture because of manufacturing defects in manufacturing. Because of the manufacturing defects, that air gaps coming to the picture. So this is the reason why, keep it in mind, if this point is not able to offer that much resisting force, then what will happen? The failure will start from this point. The failure or the fracture is going to be starts from this point. This is the reason why stress is defined at a point. Here whatever the stress is offered by the material, that should not reach the maximum limit that can bear by the material. If it reached, then what will happen? The crack or fracture, the failure will start from this point. So this is the reason why stress is defined at this point. If that stress is not more than the maximum value that can be bear by the material, then entire material will be under safe condition. Right? So first of all, this point should be under safe condition, then automatically the member will be under safe condition. So this is the reason why the mathematical definition for the stress is given as limit of the resisting force offered by the material per unit area, but delta A tends to 0. This is the exact definition of stress. Right? Stress, mathematical definition. It is defined, keep it in mind as interview point of view, this is very important, defined at a point. At that point we are drawing a state of stress. At that point we are drawing Mohr circle. With respect to that point, there are infinite number of planes are there. For all those planes we are calculating normal stress, shear stress. Right? So there is a continuity directly. So this is the reason we are assuming the total material seems to be an 100% continuous material. Continuous material is nothing but there is no internal void inside the material, right? Yes. Now, so this is the definition of stress. Now, if you look at the definition of strain is represented by a symbol called epsilon. It is defined as change in dimension. D means dimension divided by original dimension. So it may be change in length by original length, change in diameter by original diameter, change in width by original width, right? So the strain is defined as a change in dimension divided by original dimension. It doesn't have any unit. But if you look at for the stress is having the unit of force per unit area, that means Newton per meter square. Newton per meter square can also be written as Pascal. But generally we are converting into megapascal. That megapascal, 1 megapascal is also equal to 1 megapascal is also equal to 1 Newton per mm square. That relation also you need to know, right? Now, the point is, if the all deformations which are happen elastic under elastic conditions, elastic means because of this application of load, if the bar is deformed like this, then whenever if you remove the load, it has to regain its original shape completely. So whenever if you apply the load P on this member, it will be deformed. That may not be visible to our naked eye, but definitely it will be deformed. Whenever if you remove that load, it has to regain to its exact original position. Then on that property is exactly called as elasticity. If it is permanently deformed, that can be called as plasticity. Like that number of mechanical properties that you need to know: elasticity, plasticity, malleability, creep, fatigue, toughness. Right? Number of properties are there. So elasticity is nothing but it has the property of the material. After the removal of load, the member has to regain its original shape. If it is in the permanent deformation continuously, then the property of the material can be called as plasticity. Plasticity should be very important for manufacturing. Elasticity property is very important for strength of materials. Whatever the strength of material subject that we are studying, that will be under elastic region only. The whole subject will be under elastic region only. Whatever the manufacturing subject that we are studying, that the whole subject will be under plastic region only. Alright, so the differences that you need to know. This is the maximum information. And now till now we have learned what is meant by stress, what is meant by strain. As we already know, according to Hooke's law, stress is directly proportional to strain. In interview, if they asked what is meant by Hooke's law, you should not say stress is directly proportional to strain. Keep it in mind. So normal stress is directly proportional to longitudinal strain. This is very important, right? Hooke's law is given as normal stress is directly proportional to longitudinal strain. In strain, different types are there. Longitudinal strain is nothing but change in length by original length. If change in diameter by original diameter, if you take, that will be lateral strain. The ratio of lateral strain to longitudinal strain is defined as mu, Poisson's ratio. But if anybody asked in the interview what is meant by Hooke's law, you need to say the normal stress is directly proportional to longitudinal strain, or the stress is directly proportional to corresponding strain. The stress is directly proportional to corresponding strain, and keep it in mind that is also up to proportionality limit. Keep it in mind, stress versus strain diagram, this thing we are going to learn up to proportionality limit. Proportionality limit means within the elastic region, the normal stress is directly proportional to longitudinal strain. The stress formula is a P by A is exactly equal to, if you know the proportionality, you need to introduce a constant called Young's modulus. Longitudinal strain I am taking as a delta L by L, change in length by original length. From this, delta L is given as a PL by AE. So this is the formula, right? Yes. Here, lot of theoretical information we have learned, my dear, right? Just if you look at the problem, you need to understand the problem and you need to apply this relation directly. You need to solve the question up to this the gate level of question. But this is the theoretical type of information that I have discussed. From an interview point of view, this information is very important, right?